Okay, so last time we got into really titration, acid-base neutralization, solution stoichiometry. So really a lot of these are, when we talk about sort of acid-base neutralization reactions, we're talking about sort of an idea like titrations, where, for example, you add some, say, sodium hydroxide from a burette to a beaker that has maybe an acid in it, and you continue to titrate until, as we talked about and did in those experiments, you reach the equivalence point. And the equivalence point, again, is the point really where the moles of the acid will equal the moles of the base in a acid-base titration. And remember that when you react basically an acid plus a base, you get basically two things. You get a salt and water. And, for example, if you took HCl plus our sodium hydroxide, strong acid, strong base, we basically have a double displacement reaction happening. They're going to switch partners, basically, and that will get you the water. And pretty much in a strong acid, strong base combination, the water will always come from the H from the acid, and the OH basically from the base is where basically the water will come from. The salt is just an ionic compound, so that's just going to be the other two parts there coming together, a little NaCl in this case, and that would get you your salt and your water in this case. So when we do these type of problems, either a titration problem or where it's just neutralizing an acid with a base or a base with an acid, doesn't really matter which way you do it. It's really just a stoichiometry problem involving solutions. So we still follow the same steps. We still want to make sure we have a balanced equation. We still want to convert to moles. We still always, in any type of stoichiometry problem, want to determine, is it a limiting reagent problem as well? So you always want to kind of keep that in the back of your mind. A lot of times they're not limiting reagent problems, perhaps in solution stoichiometry, but you could still have that situation that occurs. Once you've determined that, or if it's not, you want to do your mole to mole relationship. And lastly, we want to convert those moles to some other unit. So really where sort of titration problems, solution stoichiometry problems sort of vary from a basic stoichiometry problem is, I would say usually at step number 2, you're probably going to use molarity and volume to get moles. So instead of maybe grams to moles using the molar mass, you're going to use the liters and the molarity. Also at the end of the calculation, that is where you're going to perhaps also use molarity. Either you may actually solve for molarity by using the moles that you got in the stoichiometry part and the volume that was given to you. The other one is you can probably solve for volume, is a very common way. And that would be using our moles that you got in the stoichiometry part and the molarity that was given to you. So I would say a lot of times those are the two very common sort of endings to these type of problems with solution stoichiometry. You could also still do, at the end, your basic kind of moles to grams as well is also an option on these. But I would say probably this is really where it's going to kind of differ, and probably the ending part here is really where it differs. The rest of it is still just a stoichiometry problem to get to the moles of what you're interested in. Any questions on any of that stuff there that we talked about? All right, so we did an example last time, so why don't you try this one here. We're looking for what volume of 0.355 molar sodium hydroxide is required to react with 125 milliliters of 0.5 molar sulfuric acid. So follow those 4 steps, see what you come up with here. So it's a solution stoichiometry. So we definitely need an equation. So we're taking sodium hydroxide, which is NaOH. That is a strong base reacting with sulfuric acid, which is a strong acid. And again, it's going to give us a double displacement situation happening where the positive guys will basically switch partners. Again, here we're going to make basically water and a salt. The water here going to come from when those guys come together. Once again, the H from the acid and the OH from the base is going to give us our water in this case. What is left over is two things. It is a sodium ion that has a +1 charge and a sulfate that has a -2 charge. So once again, we want to make sure we get the proper formula, which should be Na2SO4. Remember that when we're writing an equation like this, we want to get the right formulas down, regardless of the balancing part. We could take care of the balancing part after we get the right formulas down. And in this case, we now have the right formulas down. Get rid of some of this highlighting, maybe. All right, now that we do have the correct formulas, we want to make sure it's balanced. Otherwise, it's really no good to us. So you will need a 2 there, and I believe you will need a 2 there as well. Any questions on that equation? At this point, we could kind of look at what was given to us. We're looking for the volume here of sodium hydroxide. We do have its molarity. For the sulfuric acid, we have its volume and the molarity of it. So right off the bat, since we are looking for something for one of the reactants, it's definitely not a limiting reagent type situation. So it's a basic stoichiometry problem. We can only really get moles from this piece of information. It's the only one we can get to moles. When we think about the sodium hydroxide, if we think about the molarity equation, say for the sodium hydroxide, we have the molarity given to us. We are going to be looking for the volume. So that means really what we need to do that is the moles of the sodium hydroxide. And that's really where the stoichiometry part is going to come into play. We're going to use stoichiometry to get to those moles so that we can ultimately get to the volume. So to do that, we got to start with the only thing that we can get to moles in, which is the sulfuric acid. Remember that when we use molarity and volume, the volume needs to be in liters. So we do need to convert our milliliters into liters. So 1,000 milliliters is a liter, gives us 0.125 liters. Also remember that we do want to get rid of the big M and convert it to moles per liter. That way we can see both units, and by doing that, we could clearly see we're just going to multiply here by the molarity of the sulfuric acid. The liters here will cancel, and that will get me 0.125 times 0.5. 0.0625 moles of sulfuric acid. Remember, ultimately, though, we want sodium hydroxide moles, so this is where the stoichiometry part comes into play. So looking at the balanced equation between the acid and the sodium hydroxide, we can see that for every 2 moles of sodium hydroxide, we get 1 mole of H2SO4. So that is definitely what we want to use next here. So 0.0625 moles of the sulfuric acid. Using the stoichiometry relationship is going to get us to sodium hydroxide. So 1 mole of sulfuric acid on the bottom and 2 moles of this sodium hydroxide up on top. We'll times that by 2. Going to get us 0.125 moles of sodium hydroxide. At this point, the last thing that we could do is now use the molarity equation because we just got the moles that we needed. We have the molarity. So once again, we could solve for the liters in this case. So using our moles that we just got, 0.125 moles of sodium hydroxide. I'm going to use the molarity of sodium hydroxide here. Also going to get rid of the big M and use it as moles per liter, which I could use as like a conversion factor and just basically go opposites cancel. So I would need to put the moles on the bottom here so that they do cancel. Liters of sodium hydroxide up on top, basically dividing. You don't have to worry about the math part of it if you just do it this way because it will do it for you. And now we can get 0.125 divided by 0.355. Going to give us 0.352 liters, which if we multiply by 1,000, we could get it into milliliters, which would be 352 milliliters. Again, really, you could leave it in any unit in this question because it didn't specify what unit. But if you want to convert to milliliters like the other volume, you can. This is, again, really just stoichiometry like we've done a ton of times up to this point. Step 1, balance the equations. Step 2, convert to moles. Step 3, do the mole-to-mole relationship. And step 4, take those moles into some other unit. So it is still the same 4 steps, just different ways of getting moles and different ways at the end using those moles, getting something different like volume here, exact instead of like grams or something like that. Any questions on the steps there? All right, so try one more here. In a titration, it requires 63.5 milliliters of calcium, 0.35, I want to say that right, 0.375 molar calcium hydroxide to reach the equivalence point of 95.5 milliliters of hydrobromic acid. What is the molarity of the hydrobromic acid? So again, a titration type problem, basically the same type of problem we've been doing here. All right, so let's take a look. Once again here, we're going to have to start with an equation. So calcium is +2, hydroxide is -1. So calcium hydroxide should be CaOH2. Going to react with hydrobromic acid, that is HBr. Once again, this is an acid-base reaction, so pretty safe bet you're going to get water in our double displacement here. So we will get water, again, as these two guys swap, and these two guys will swap. So that is a calcium with a +2 charge and a bromide with a -1 charge. That gets us CaBr2 as our sort of other product there. At this point, now that we have our right answers down there, our right formulas, we can then balance it. If I can find my eraser, we can balance it maybe. There you go. And it looks like perhaps in this case, we will need, what do we need there? Calcium, bromine, need like a 2 there perhaps, and a 2 there, I think in this case. All right, we now have a balance. We can look at what was given to us. In this case, we got 63.5 milliliters of 0.375 molar. For our HBr, we have just the volume, and we are looking for the molarity here. So definitely not a limiting reagent. We could get moles of this guy. We know again that molarity is moles per liter. So we're ready for the HBr, have the volume, just need to do a conversion on it. We're looking to solve for the molarity. So once again, we're going to use stoichiometry here to get to the moles of the HBr so that we'll be able to solve for what we're looking for. Once again, just like in the last one, we got to convert our volume here into liters. So 63.5 milliliters, 1,000 milliliters is a liter, going to get us 0.0635 liters. We then can use the molarity, and once again, we'll get rid of the big M, and we will use it as 0.375 moles per liter. Liters do need to go on the bottom here, or does need to go on the bottom, so that they do cancel here. So again, we want to get rid of that big M when we're doing the calculation. So that's going to give us our moles of calcium hydroxide, 0.0635 times 0.375 gets us 0.02381 moles of calcium hydroxide. Again, we're ultimately looking for the HBr, so this is the stoichiometry part of the calculation. We're going to go to the equation there and find our relationship, and we can see that 1 mole of calcium hydroxide gets us 2 moles of hydrobromic acid. So using our number from our top calculation there, we're going to do the stoichiometry part here. And again, we want to go with calcium hydroxide on the bottom so that they cancel in the moles. And up on top will be our moles of HBr. So those guys will cancel. So that'll get us here, looks like 0.04763 moles of HBr. At this point, when we think about finding the molarity, we just got the moles of the HBr. We have the volume, so we have everything that we need to calculate the molarity. But once again, we do have to do one more conversion of the volume that was given to us for HBr so that we can put it into liters. So we'll take our 95.5 milliliters, convert that guy into liters so that we could use it in the molarity equation as 0.0955 liters. Now we have everything that we need. The molarity would be our moles up on top divided by our volume for our hydrobromic acid. And that will get us here, looks like 0.4, I'll call it 99. And you could leave it as one of two ways. You could leave it as moles per liter, or 0.499. You could bring back the big M at this point for your HBr. Once again, pretty much same 4 steps. Balance the equation, convert to moles, mole to mole relationship, and moles to some other unit basically here. Any question on any of those steps along the way? So if we could get and see a pattern, really same steps, just slightly different how you get some of the numbers. Since we're using solutions, molarity, volume plays a pretty big role. Any questions on solution stoichiometry, titration type problems? Yeah. The last thing we're going to talk about in this chapter, just briefly, is another unit of concentration, which is known as normality. And normality is actually the equivalents per liter instead of moles per liter. Normality is equivalents per liter. It is actually abbreviated with a capital N. And we could calculate the equivalents for an acid or a base based on how many H pluses or OH minuses it will actually kind of donate in the process when it breaks apart. And so, for example, if you have HCl, it will make H plus and Cl minus. It basically has one H plus, which means you, for every 1 mole of HCl, you get basically 1 equivalent. And that's basically how much H plus it will donate. If you had something like sulfuric acid that we just kind of did there, you will have 2 H pluses and a sulfate, which means for every 1 mole of your H2SO4, you will actually get 2 equivalents because of that. Same thing with a base, but it would be just doing your hydroxide. So this would give you a sodium ion and 1 hydroxide. So basically in 1 mole of sodium hydroxide, you would have 1 equivalent here of OH minus. So the equivalents basically are how much H pluses or OH minus are there. A very common thing that instead of molar mass, sometimes in, say, titration type problems in acid and bases, sometimes they calculate what's known as the equivalent weight of an acid or base. And that's the mass in grams of 1 equivalent of acid or base. So it's really grams per equivalence instead of, say, grams per mole, which is typically what molar mass is. And that's usually what we calculate. So common strong acids, as we talked about, hydrochloric acid, nitric acid, sulfuric acid. By the way, perchloric acid is another strong acid. Hydrobromic acid, hydroiodic acid is also some strong acids. Sodium hydroxide, potassium hydroxide, you know, a lot of these guys here, calcium hydroxide, strontium hydroxide. These are some strong bases as well. So HCl, like I said before, can basically give you one equivalent because it will produce one H plus when it breaks apart. So for example, if we wanted to calculate the equivalent weight in grams per equivalent of this acid, we could actually start if we just have the formula with the molar mass. And if we do the molar mass from the periodic table, that is 3 times 1.008 grams per mole, plus our arsenic there, which is something there. 7492 looks like. 7492 grams per mole, plus 4 times 16 grams per mole for the oxygen. So that's going to give us a molar mass here in grams per mole of about 140, we'll call it 142, I think, grams per mole. So basically, we have the molar mass, and when we look at this acid, this is a triprotic acid, which means it can donate, in this case, 3 H pluses when it breaks apart. And that essentially means that in 1 mole of this acid here, we will actually have 3 equivalents, again, because it's able to donate basically 3 H pluses. So we really could just do kind of like a dimensional analysis conversion here. We have 142 grams per mole of this acid. We could use our relationship that we just see there above and go for every 1 mole of this acid, we get 3 equivalents. The moles will cancel, and that will get us 142 basically divided by 3. Will give us an equivalent mass of 47.33 grams per equivalence. So this is a common way sometimes, we'll say not used very much these days, normality, but you can calculate something like equivalent weight or equivalent mass rather than molar mass of acids. It's sometimes used along the way. Any questions on that there? Now, normality, as I mentioned before, is really equivalence per liter, and it's kind of like molarity. Again, instead of moles, we're using these equivalents per liter, and you can rearrange it, kind of the same idea as molarity when you do that. So if we had something like this, which is 2.5 molar sulfuric acid, and we want to know what is the normality of it, we would kind of take the same approach. You want to kind of think of it almost like a dimensional analysis conversion problem. Once again, that 2.5 molar means that I have 2.5 moles of sulfuric acid per liter of sulfuric acid. Now, normality is equivalence per liter. So really, if I just think of this like a conversion problem, my bottom is good to go. I really just need to convert the top part from moles to equivalents. And that's going to be based off of the acid that we have here, which is also sulfuric acid. And again, as we've seen, when that breaks apart, we get a couple of H pluses and a sulfate. That means that in 1 mole of sulfuric acid, we will get, because you get 2 of those guys, 2 equivalents. And really, you just want to kind of use it as a conversion factor. So we want to get rid of moles. So on the bottom, we'll go 1 mole of sulfuric acid. Up on top will go our 2 equivalents. The moles will cancel, and we get a normality here of this acid of 5, basically. Equivalents per liter are 5N. Question on that there. So obviously, if you had to calculate the normality, you could just figure out the equivalents, you can figure out the liters, divide it out, and you'll get the normality as we got here. Again, not used all that much these days in industry when you buy by acids and bases. Sometimes they still give the normality. For example, we might have it in lab today, but if you look at those little square box that we use with the sodium hydroxide when we did titrations, if you look on the label, you'll sometimes see the normality given on those things. So they still kind of using that, but I would say molarity definitely is something that we use a lot more. Any questions on normality there? All right. We're going to wrap up. That is going to wrap up this. Go off here to chapter 16, which is the second to last chapter. So that's got to be good, I imagine, right? We're running out of chapters. So acids and bases in this chapter. We're going to talk about. So let's talk about them. So acid and bases were first recognized, for example, acids have typically sour taste. There's acids in common things, obviously, like vinegar, which is acetic acid, lemons, which is citric acid. Bases are characterized by a bitter taste and they feel very slippery. For example, hand soaps, drain unclogging solutions like Drano are bases. You obviously don't want to taste either of these things in the lab for sure. Bases are also referred to as being alkalis. And if something is basic, it is referred to as being alkaline, really means basic. And that sort of name and these names should be familiar to you as group 1 and group 2 on the periodic table. That's your alkali metals, your alkaline earth metals. So group 2, group 1, and 2 on the periodic table is where a lot of strong bases come from. So if you look at group 1 and group 2, if you look there, you got like lithium, sodium, you got potassium, you hang a right there to calcium, strontium, barium. If you kind of go this way in group 1 and group 2 and you pop a hydroxide on those guys, you're going to probably have a strong base. And again, that's the alkali metals, the alkaline earth metals. So a lot of strong bases come from those two groups on the periodic table. Actually, a lot of acids actually come from the non-metal region on the periodic table is where a lot of acids come from when you react them with water. So if you have any of those guys on the upper right of the periodic table, like nitrogen, oxygen, and those sort of area, and you have oxides, those guys with oxygen, and you add water to it, those where a lot of acids come from. So for example, if you had water added to CO2, that makes carbonic acid. And again, a lot of nonmetals, when you add water that has oxygen, will get you your acids. Now, sort of an early definition of acids and bases was one that was done by Arrhenius. He did a lot of work with electrolytes. Electrolytes are substances that when they go into water will break apart into ions. So you got a bunch of ions floating around. And he basically defined a acid as a substance that has the ability to produce hydrogen ions in solution. Hydrogen ions are H plus ions in solution. What we're talking about here is free floating H pluses. So just floating around freely in the solution, not attached to anything, basically floating around. H pluses in acid-base chemistry are also sometimes referred to as a proton, and that is because hydrogen has one proton, one electron, and no neutrons, which means when it loses an electron and becomes positively charged, like H plus, it only has a proton. So it is sometimes also referred to as a proton in acid-base chemistry. In addition, H plus and H3O plus, which is a polyatomic ion, that is the hydronium ion, are essentially the same thing. They are used interchangeable in formulas. They are also used interchangeable in equation and reactions. I personally go with H plus most of the time when we're talking about an acid. A lot of books and stuff nowadays will use H3O plus. So really anywhere I say put H plus, you could change it out to H3O plus. It's basically the same thing. So it's really the acid part of the solution, and it's symbolized either by H plus or H3O plus, basically floating around. He defined a base as something that has the ability to produce hydroxide in solution. Same idea here. We're talking about the ability to produce free-floating hydroxide ions in the solution, not attached to anything. As we'll talk about the sort of proportion of H plus to OH minus guys that you have floating around in that solution will help you determine whether or not the solution is acidic, basic, or neutral, depending on sort of the proportion of those guys that you have freely floating in that solution. As you could probably imagine, if you have more H plus floating around in the solution, it's going to be acidic most likely. If you have more OH minus ions floating around freely in the solution, it's going to be more basic. And neutral will pretty much mean you got about the same of those ions floating around. H plus and OH minus will give you basically a neutral solution. So if you take hydrogen chloride gas and you dissolve it in water, you will get hydrochloric acid, which is a strong acid, and will completely dissociate into H plus and Cl minus. And sodium hydroxide dissolved in water will produce these ions. Hydrochloric acid is a strong acid because when it goes for a swim in water, it will 100% break apart into ions. And because of that, you're going to produce, when you put a bunch of HCl in there, a lot of H plus into that solution really quickly, and that's going to make it more acidic. Same thing with the sodium hydroxide, which is actually a strong base. When that goes for a swim, it is going to 100% break apart into ions. And because it does so, all it needs to do is go for a swim, and it will produce a lot of hydroxide ions freely floating in the solution, and that will make it a base. And that's why they're both a strong acid and a strong base, because really all they have to do is go for a swim, and they're going to break apart, and you're going to get a lot of H plus or a lot of OH minus really quickly produced. And it doesn't have to do a lot of work to do that. It's just they basically have it on them to release, and that's why it will be a strong acid or a strong base. Now, the Arrhenius sort of idea of acid and bases was a really good one. It was a little bit limited, as he did account for really one type of base, which is solutions that have hydroxide in them, like sodium hydroxide. But for example, not all bases actually have hydroxide on them, if you will. So for example, NH3 is a weak base. And it's a weak base because when NH3 reacts with something like water, what's it going to do is it's actually going to take an H plus from the water. And the result of that is you'll make NH4 plus, and you will make some hydroxide ions. Now, it is still considered a base because it's able to produce hydroxide. It does not have OH on it to start with, but it has to go do a little reaction to produce hydroxide when it reacts with water. That's also why NH3 is a weak base compared to what we just looked at, which is sodium hydroxide, which doesn't need to go find anybody. It just needs to go into the pool and break apart into these ions and will produce hydroxides carrying it with it, if you will. So that's why NaOH, or sodium hydroxide, is a much stronger base than ammonia. Ammonia's got to go do a little reaction and produce it. It's actually a weak electrolyte, a weak base. It will mainly stay together and just do that reaction a little bit. But sodium hydroxide is just going to basically break it apart. So when we talk about acid and bases, we kind of oftentimes talk about it in the terms of what's referred to as the Bronsted Lowery definition of an acid and base. And a Bronsted Lowery definition of an acid and base is an acid is a proton donor. So if you have something that's an acid, it will donate a proton, basically give it away. It's really important on this is it is actually not just the H, but the plus charge comes with it. So that affects the overall charge of where it ends up, the H plus, and also where it left. So it affects it, that positive charge with it. A base is a proton acceptor, so it will accept a proton. So for example, if we actually look at the example I just wrote on there with the water, for example. The NH3 is a base because it's going to accept the H plus here from the water. And that means actually the water here is acting as the acid in this sort of reaction. So water is acting as the acid, NH3 is acting as the base. And the consequence of sort of the Bronsted Lowery definition is actually on the other side of the arrow, you create partners. And for example, when the NH3 gains the H plus, it makes NH4 plus on the other side. So those two things are related to each other. And this is what is known as the conjugate acid. And the conjugate acid comes from a base that has accepted an H plus to it. And if you look at the acid on the left, which is water, it is related to the OH minus on the other side. And that is what is known as the conjugate base. The only difference between the base and its conjugate acid and the acid and its conjugate base is this 1H plus, that 1H plus that has been donated, and that is the only difference between it. When you go from the base to the conjugate acid, it has one more H plus. When you go from the acid to the conjugate base, it has one less H plus as partner. So what I was talking about earlier is the effect of accepting an H plus. So if we look at NH3 here, it is neutral. When it accepts the H plus on the other side, it has one more hydrogen, but now becomes one more positive because it gained not just the H, but the H plus part of it. When we look at the water on the left, it is neutral. When it loses the hydrogen, it has one less hydrogen over here. And it goes from being neutral to being negative, because when you lose a positive, you now become one more negative because you have one less proton and more electrons. So you become more negative, as like we see with the other guy, he becomes more positive when he gains that proton. So he actually becomes negative. So it's really important to understand that it's not just the hydrogen, but that plus does affect both. What happens when it accepts the hydrogen and when it basically donates the hydrogen. Any questions on that there? So again, as I just mentioned, we have some partners that occur. Again, the acid on the left will always partner up with the base, conjugate base on the right. The base on the left will always partner up with the conjugate acid on the right. In this case, again here, the acid, which is HA, is going to be donating the H plus over. The result of that there is that acid will lose a hydrogen and then becomes one more negative, so it becomes A minus on the other side. The water here gains the hydrogen, and that means it gets three hydrogens there total on the right and becomes one more positive because it gained a positive charge in this case. When you are looking at an equation, the regular old acid and bases are always found on the left-hand side of the arrow. Your conjugate partners are always found on the right-hand side of the arrow. So that is where you find those guys on the right. And again, your regular acid and bases. Once again, the only difference that can be for them to be partners is that single H plus that is being transferred. If you're looking at two things and trying to determine are they partners with each other, if it is more than one H plus, they are not partners. So that can be the absolute only difference between two things. If you're looking at them trying to determine are they conjugate acid base pairs, it can only be that H plus. So here again, if we look at water in this case with our HCl, so this is going to be our acid and our water here is going to be our base. and that means the acid is going to donate that H plus over. When it does so, the acid will lose an H plus and be left on the other side as the conjugate base, as Cl minus. The water here on the left will accept the H plus and be the base, and on the other side there will be H3O plus, which is our conjugate acid in this case. Once again, the only difference between those two things is that one H plus is being transferred. Any questions on that there? All right. And again, this is sort of what's happening. H plus being transferred from the acid to water, which is acting as the base in this case. And obviously our hydrochloric acid is our acid, and that makes our hydronium ion that we were talking about there, H3O plus. So why is like H3O plus, which is this guy, and H plus the same thing? What we're really looking at here is really an acid dissolving in water, basically, and breaking apart. You can also write this equation without the water, and it is perfectly fine to write the equation like this. And because I didn't include the water, I get H plus. When water is included in the equation, you get H3O plus. Again, both of these things are the same thing. They are basically representing the acid part of the solution. So sometimes people, when they write an acid really just dissociating or breaking apart in water, they'll put the water in there and you'll get H3O plus on the other side. Or you could do it without the water and just write it breaking apart, and you will not get the H3O plus. You will just get the H plus. They're basically the same reaction and same thing happening here. All right, so take a moment here and for each of these, decide if they represent a conjugate acid-base pair. Okay, so let's take a look. So the thing that you're really looking for to see if they are related to each other by Bronsted Lowery definition of conjugate acid-base pairs is basically just a difference of one H plus is really what we're looking for. So if we look at this guy here and this guy, however you want to look at it, if you take off the H here, you're there. And if you take off the plus, you become one more negative. So those are pairs. That is the only difference between them. You can also put the H plus on the guy on the right there, and you'll get the guy on the left. So as long as you could either take off an H plus from one thing and get the other guy, or put on an H plus, you will have pairs. Here we have on the second one, HCl and ClO minus. It definitely is a difference of an H plus, but the problem here, it's also a difference of an O, and this guy does not have an oxygen. That means that this is not a pair. Again, it can only be one H plus difference. If we look at the next set there, again, however you want to kind of do it. If you want to take off an H from the guy on the left, that's going to take off that. And remember, when we lose the positive, we become one more negative. So it started at -1. It will end up at -2. And that means that this guy is a pair, as they basically are the same. And lastly here, this guy would also be a pair, as if we take off the H, we get that, and the plus means we become one more negative. So looks like everybody here are acid conjugate base pairs except number 2 there. Any questions on that there? Okay. All right, so why don't you do this for each of the following, write what the conjugate base would be if you started with each of those. Okay, so let's take a look. So once again, it is just the H plus. The key is, should you put the H plus on or should you take the H plus off is really what you want to decide here. So the way you could help you decide is if you understand the relationship we talked about earlier, which is you have your acid plus your base on one side, and then you have your conjugate acid and your conjugate base on the other side. And the relationship is the acid on one side will partner up with the conjugate base on the other, and the base and the conjugate acid will partner up. So in this particular case, we're looking to write the conjugate base, which is here. So if we're not sure what we're looking at, if we just kind of follow it backwards, that means that each of the things we are looking at here are acids. And if you could determine that each of these are acids, all you have to do is go by the Bronsted Lowery definition of an acid, which is it will donate an H plus. So here we would actually want to take off an H plus in each of these cases. So again, if we do that and we remove the H plus, that will leave us one hydrogen and an S. Again, it was neutral to start with, so the positive charge will make us now one more negative as we lost the positive charge. Starting with this guy, we would get rid of the hydrogen, which would leave us at just an S. And again, we're actually starting at -1. And again, when we lose the positive, we become one more negative. So it goes from -1 to -2 in this case. Here, we're going to lose a hydrogen, so that will leave us two hydrogens. This was neutral, which means it becomes one more negative, so it'll be something like that. And lastly, here we will lose one of our hydrogens, which would leave us one hydrogen, an S, an O, and a 3. Also neutral will then become negative. Any questions on any of those? So why don't you try this guy here, a little HCO3 minus. Why don't you write the conjugate acid? And why don't you also, starting with it, write the conjugate base? So in each case, you're starting. Start here with conjugate acid. If you're not sure, conjugate acid is here. If I work backwards, that means in this particular case, this guy is going to act as a base, which means he's going to accept the H plus. So in this case, we actually will put on the H plus to this guy. And if we do that, we end up with two hydrogens, a CO3. +1 -1 gives you 0 when you add them together, and we get no charge in this case. Now, if we look at the conjugate base, like we had in this problem, if we want the conjugate base working backwards, in this case, this guy will actually act as an acid, which means it will donate the H plus. So we're going to get rid of the H plus, basically. And that will leave us a carbon, an oxygen, and 3 oxygens. And we were -1 to start with, so we'll become one more negative, and that will be -2 and make carbonate in this case. This guy, as you can see, can act as an acid or a base. And a lot of things that have a hydrogen and like a negative charge have the ability to do that. Water, by the way, also has the ability to do that, act as an acid or base. That's what's known as an amphoteric substance, something that could act as an acid or a base. Any questions on that there? All right, we'll lay it up there for today.